how black holes shine, how they can produce high energy emission from near the horizon. Just to give you some perspective, although I think with this crowd I probably don't have to motivate, but why do we care about black holes? Right, there's physics motivation, like we want to come up with a theory of quantum gravity, and black holes seem to be a good laboratory to test some of those ideas. It's obviously very hard, otherwise we would have done it already. But so we want to focus on what happens near the horizon. We can see light coming from there, and that could give us some information about how gravity behaves, and if we can see where Einstein's theory sort of fails. And the other one is in a more astrophysical or cosmological motivation. We know that we have many active galactic nuclei, but we pretty much don't know how they got there. How did the supermassive black holes in the centers of galaxies grow? How do they accrete? How do they interact with the environment, both outwards, like what kind of AGN feedback do you have, and inwards, like how is accretion getting all the way from larger scales to the horizon? We pretty much don't understand any of those questions. Understanding them gives us a view on cosmological history, pretty much. So if we look at the sky, this is a Hubble Deep Space image. We see many galaxies. I think there's one star here, but there is no indication that there is a black hole in the center of these galaxies. There is no particular way of knowing that there would be anything special here in the center of these galaxies. Until we started looking in radio, then we started seeing those huge plumes here, jets, highly relativistic outflows that are so energetic that they light up in the radio. And pretty much, if by thinking about an energy argument, like the energy that's coming from this huge plume can only be powered by something that's extremely powerful. So that's an indirect indication that there has to be something either very exotic or a black hole, if you consider black hole not to be exotic anymore. And the same goes for the light that comes from the center. You cannot really explain that light with anything that's not a black hole or that is not something special that we haven't detected yet. So to understand that a little bit better, we need to, let me switch off these messages. To understand that a little bit better, we need to model the plasma physics near the black hole. And the regime of plasma physics there is pretty clearly relativistic. The relativisticness of plasmas is indicated by the sigma parameter, and sigma is pretty much the magnetic energy over the rest mass energy, the ratio between magnetic energy and rest mass energy. And in any terrestrial plasma, like in the Earth's magnetosphere, in a tokamak, in a fusion reactor, and also around the sun, the sigma parameter is smaller than 1. So, and we can use our Newtonian approximation, but around neutron stars and also in black hole magnetospheres and jets, the sigma can get very, very large. In accretion disks, Newtonian approximation would probably still be fine, except that, of course, you have like Einsteinian gravity there, but the sigma is maybe order 1 in a disk. So what does this mean? What are typical conditions in the disks that I will be talking about? So it's low luminosity active galactic nuclei, if you want, or MD7 Sagittarius A star. The plasma is collisionless or near collisionless, meaning the Coulomb collisions are negligible, and the mean free path of an electron is very large. It's larger than the size of the system, larger than the disk. It's magnetized, the sigma is large. If sigma is large, it means that your Alfvén speed, say the typical speed of waves in the plasma, is of the order of the speed of light. And you have Lorentz factors that are much larger than 1, both for individual particles and for the bulk motion of the flow. On top of that, you have a huge scale separation, a typical particle motion. So the Larmor radius of a particle along a magnetic field is much smaller than the system size. So what this gives you is a large reservoir of magnetic energy. Sigma is high. We have a lot of magnetic energy, a lot of B squared, and a collisionless nature. Particles can travel without thermalizing. So it seems to be ideal to accelerate this plasma and power this high energy radiation. But now comes the main difficulty. a magnetized plasma in itself doesn't necessarily radiate. You need to somehow transfer that energy down to the kinetic scales of the particle. Let's say you need to demagnetize the plasma. You need to dissipate the magnetic energy into something that gives us observable radiation. How that happens is a very difficult question to answer because of the high energy, and a magnetization needs special relativity. You need general relativity due to the gravity of the black hole. You need pretty much kinetic theory because the plasma is collisionless. So you need to treat the particles as particles. You need radiation and quantum electrodynamics pretty much because of the high energy emission mechanisms, inverse Compton scattering, pair production. And all of this needs to be solved numerically because analytically we cannot track it anymore. And because of this large scale separation, you need very high resolutions. So this is a problem we cannot yet solve, but we can approximate it from different sides. So the issue here is not so much that we don't know which equations to solve. It's not like we need to still come up with some string theory equation which describes these processes. We do know the equations. It's the Vlasov equation. It's just it's hard to solve. So the Vlasov equation is like a Boltzmann equation where for the force term you plug in the Lorentz force. So this is the evolution of a distribution function of particles, whatever you want, electrons, positrons, protons, heavier particles that are driven by the electromagnetic force pretty much. The electromagnetic force, the electric and the magnetic field you get from Maxwell's equations. So those two are coupled. But then those particles, they're typically charged. So charged particles can form currents if they move, and charges. And if you remember Maxwell's equations, the charge is a source term for the divergence of the electric field, and the current is an input in Ampere's law. So these equations are coupled, and you need to solve them together. So this gives you a multidimensional, nonlinear, many-body systems, billions of particles. You can solve it with particle and cell. You can also solve this equation with the Vlasov solver, like continuously solving it, but it's extremely expensive. So to give you an idea why, if you look at the Event Horizon Telescope results, this is MED7's jet in the left top corner, measured at 230 gigahertz. The length of the jet is of the order of 1,000 light years. If you then zoom in all the way to the EHT image, it's a fraction, like 10 to the minus 3 light years. So there's already a huge scale separation there. But then if you take a typical magnetic field strength, say 100 Gauss near the horizon, then the alarm radius of the particle is about 10 to the minus 11 Schwarzschild radii. So 10 to the minus 11 times the radius of this black region. So we're dealing with 17 orders of magnitude in scales in this whole system that you need to solve. So there is no simulation, no kinetic simulation that can cover all of this so far. There is not even a kinetic simulation of an accretion disk. There is one. I'll tell a little bit more about that later, but it has a lot of assumptions. We cannot easily separate those scales though, because they interact nonlinearly through instabilities, Kelvin-Helmholtz, Rayleigh-Taylor, name your favorite instability, through turbulence, turbulence cascades, energies, or dynamos for the other way around. For example, you can start with small magnetic fields and they grow to macroscopic sizes. And all of those effects are important in connecting the scales. Now, magnetohydrodynamics is, in principle, in its ideal form, a scale-free theory, and it can capture global dynamics of jet launching and accretion onto black holes. It's clearly not capturing everything, but it's capturing much of the essence of the accretion. So these are the general relativistic magnetohydrodynamics equations. On the left, you have mass, energy, and momentum conservation. This is a shorthand covariant form of let's say Navier-Stokes or Euler equations, if you wish. And these are the same Maxwell's equations as I showed before, just now in a generic curved spacetime. So typically, ideal MHD is assumed for these type of accretion models. But MHD is in principle plain wrong. It assumes that the plasma is collisional, so not collisionless. And it assumes, due to that collisionality, that you're dealing with a single temperature Maxwellian. In other words, electrons and protons have the same temperature, they thermalize. It's wrong in the jet, it's wrong in the disk, but it can still tell us something meaningful, as I will show you later. Another issue, which is important later for what I want to talk, is that what I want to tell is that ideal MHD assumes that the plasma is a perfect conductor. In other words, you can always hop into a frame where your electric field is zero. Electric field is equal to minus V cross B. So if you hop into the frame that moves with that velocity, you get a zero electric field. Electric fields are the particle accelerators that we care for. A magnetic field doesn't accelerate, it doesn't do work on a particle if a particle is in a Maxwellian. So what can we still learn? Let's go back to Blanford and Znayak. They came up with a theoretical picture of what magnetic fields can do around the black hole. If you have a spinning black hole, you have field in the colloidal plane. The black hole is spinning here, so the field inside the ergosphere gets sort of wound up, as you can see here, and you create an out-of-plane magnetic field, B phi. You create an electric field, so you create a pointing flux in E cross B, and that pointing flux is what launches an outflow, which we call a jet. This has been simulated, for example, by Sacha Tchaikovsky, one of the first people to simulate it, many others afterwards. Where you see exactly this happening. You see an accretion disk here with colloidal magnetic field. The black hole winds it up, and you get a polar jet in the green region. This seems pretty accepted mechanism for what happens around the black hole. There are also other ideas around that also make a lot of sense. So this is not the only thing that can happen, but this is what I want to focus on today. So if we look at the EHT image again, what we can learn from measuring the flux and actually looking at the type of flux that the simulation would give you is that the magnetic field strength at a few RG is roughly, I think it's 30 Gauss, and that matches with the jet power according to this Blanford-Znayak mechanism. If the jet power, the equation from Blanford-Znayak would give you the magnetic field on the horizon, which is roughly 100 Gauss for the observed jet powers. There's some uncertainty in here. Take this as an order of magnitude number. But the nice thing is that the EHT flux measurement and the jet power both give you this value on the horizon. It could be 10, it could be 1,000, but it's nice that it's consistent. As I already said, the macroscopic size of this, let's say, ring of the Schwarzschild radius roughly is about 10 to the 8 kilometers. And the microscopic size of the emitting electrons is of the order of a kilometer. The mean free path is larger than about 10 to the 8 times the Schwarzschild radius. So again, like huge scale separation. Plasma is collisionless. Particles can accelerate. Non-thermal effects are important. Particles can accelerate out of the Maxwellian, it's those electrons that are radiating the emission that we're seeing. So we have a problem there. MHD not the right theory. I already said that because you're not incorporating those physics, so you don't know pretty much the temperature of those electrons. Right. So luckily, there's more information. We can look at other wavelengths than the EHT, and that has actually been done long before the EHT had its results out. And this is these are gamma ray flares and X-ray flares from M87, so the first EHT target. And you see that M87 flares and the gamma rays every so many years. And here you see the X-ray components, and the X-ray component here comes from the NOT, from HST1. But here you see gamma ray flare, and there is no X-ray emission from the NOT, but there is X-ray emission from the core. So this tells you that those gamma rays may very well come from near the event horizon. So you need to think of like what could be that acceleration mechanism near the horizon. We have more information. We have polarization information. I'll get back to that later. We also have Sagittarius A star. I may say something about that towards the end of the talk if time permits. And from Sagittarius A star, we also have a different wavelength flares. We have X-ray flares, we have infrared flares. Infrared flares even have been measured to orbit around the black hole by the gravity collaboration. And I would argue that systems in between Sagittarius and M87 in terms of mass are also very interesting to look at, but they're a little bit understudied. But for example, Andromeda M31 shows X-ray flares as well, and the same holds for M81. And they're well observable, and their timescales are longer than Sagittarius A star, but much shorter than M87. So they're kind of nice to study. We cannot resolve them with EHT necessarily, but for flares, they're pretty nice laboratories. So the main questions that people try to answer maybe are what powers jets, what drives accretion, and how can you get such a broad radiation spectrum up to those extreme energies. And well, now we have this additional information with flares coming from near the horizon. This is Centaurus A. We haven't observed any flares as far as I understand, but I'm just trying to point out that there are two locations for those flares in the larger jet or from near the core, and I want to focus on the core. And an often invoked model for these flares is magnetic reconnection, so similar to solar flare. Here you see a solar flare. So what happens on the sun is pretty well studied and observed is that the loop of magnetic field can sort of build up, and then it can reconnect on itself. The foot points of the loop can reconnect, and then particles are accelerated and they emit higher energy photons. So now the main question is, how does that happen around the black hole, or can that happen around the black hole rather? And what can it teach us about the black hole? And to do that, as I already argued before, you need to do pretty extreme plasma physics because you need all, well, GR, QED, and so on. So the nice thing about solar flares is that the reconnection of field lines has not only been conjectured, but it has been observed by now. So this here in magenta is a field line, and in yellow as well, and you see them coming closer to each other. And here they found each other and they reconnected, they formed an X point. So the blue field lines you see have a clearly different topology than these here. And exactly here in this X point is where you liberate a lot of magnetic energy that goes into the particles. And you see those particles actually lighting up in what we think are plasmoids. I'll get back to that later. It's also pretty well understood from local box simulations. I mean, Maria was one of the people pioneering this with Lorenzo Cironi, and there is a group in Boulder, Greg Werner, Dimitrius Dansky, and Sasha Filipov, doing these types of simulations from first principles. So this is really solving this kinetic set of equations, incorporating all the physics here, even radiation. And what you see is this is a box, and this is the same box, just two different snapshots put on top of each other, and just anti-parallel field, two-dimensional, and the field lines approach each other into such X points, and the upstream field has a high magnetization, high sigma. The inflow is the E cross B velocity, and you create an accelerating electric field, an out of plane in EZ of about 0.1 times the upstream magnetic field. So it's a pretty efficient accelerator. But you see more than just the theory. You actually see that those current sheets, those reconnection layers, they tear up and they form those tiny plasmoids. Plasmoids can merge, grow larger, and form these huge containers that can be filled with those energetic particles that are then radiate. Depends on the radiative regime whether the particles will radiate before they end up in the plasmoids or not, and I may get back to that later. But for now, what's most interesting is that there is a relation between the upstream magnetization and the Lorentz factor that a particle can reach. So the higher the sigma, the higher the Lorentz factor of the accelerated particle. And you see this here in the distribution function. For higher sigmas, you get higher energy particles. And so this is nice because we're dealing with a highly magnetized system. So in principle, you would say you can accelerate particles up to Lorentz factors proportional to that magnetization. At that point, radiation comes into play, which is a problem that's been studied at the moment in great detail, but there is a lot of potential, let's say. Now, magnetic reconnection in MHD is a whole different story. It can be captured if you add an explicit resistivity to your set of equations, and that's what you see here. So this is an MHD simulation, and you see that by eye, like qualitatively, it looks fairly similar to this particle and cell result. You get plasmoids, different sizes, and so on. And if you have a small enough resistivity, the reconnection is fairly similar to this collisionless regime, with the main difference that the reconnection rate is about 10 times slower. So that's something important to keep in mind. The rate of energy conversion from magnetic to kinetic or thermal is 10 times slower in MHD than it is in a collisionless regime. If you play with your resistivity model, you could potentially change that, but it's very much a non-trivial problem. And there's a student in Amsterdam, Sebastian Salvi, who has been working on that. The nice thing about MHD is that it's much cheaper than particle and cell, and with adaptive mesh refinement, so zooming in, you can have a picture here, zooming into the dissipation regions, you can actually resolve them without having to resolve the upstream variable. With particle and cell, that's not really possible. You need to resolve the whole box because you need to capture this Larmor radius everywhere for the code to give physical results. So with MHD, we can definitely learn some things as long as we keep in mind that we're not capturing all the physics fully. Same holds for ideal MHD. We were talking about that just before. You can capture reconnection in ideal MHD as long as your resolution is high enough. The mechanism for the resistivity is numerical. It would happen on the grid scale. But magically, or maybe not magically, it gives very similar results. It gives same reconnection rates as resistive MHD. So if you're a plasma physicist who wants to understand this carefully, I would always say like use a resistivity. But if you're an astronomer who wants to have some basic reconnection in their simulation, you can get away with ideal MHD. Happy to elaborate. I would need another hour. So back to those flares from MD7. I showed this already before. This is the X-ray flux. We see concurrent X-ray and radio flux from the nucleus, which tells us the emission may come from near the horizon. And interestingly, the variability timescale is of the order of days. And by simple causality argument, that means the emission region is of the order of a Schwarzschild radius. That's a very simple argument. Beaming, lensing effects may be very important, but it tells us at least that it's interesting to look near this event horizon. Going back to the solar flare problem, there is an issue. And Ashley Bransgrove, a PhD student at Columbia, who's now a postdoc at Princeton, looked into this. The no-hair theorem pretty much tells you that a black hole is not allowed to have a magnetic field loop. It would be considered hair. It would be considered a piece of magnetic information. So what does a black hole do? And it's what Ashley studied. What does a black hole do if you put a loop on it? You saw here, and let me play the video again. If you look quickly, you see that it starts out with a loop on the black hole, the dipolar field. The loop very quickly opens up. So there's no accretion disk here, just a black hole with a loop and some plasma. It opens up and it forms what we call a split monopole magnetic field. So the field lines sort of get cut open, and then these field lines go outwards to infinity. These come from infinity into the black hole. And in any possible configuration of field that you could consider on the black hole, it will always go to this split monopolar geometry. Reconnection. It's reconnection. Yeah. You need some non-ideal physics for field to open. So you could argue that reconnection solves the no-hair problem. Or you can do this, and this was indeed with some resistivity. We also did it with general relativistic particle and cell, but you can also do it with ideal MHD. Then it's numerical resistivity.
So how do you hold the flux over? And why doesn't everything stay?
You mean in the split monopolar stage, or in
this simulation?
Yeah, no, I understand, but like initially or in the late stages? Well, initially you
said it there.
You put a dipole and then it opens up. I mean, it doesn't. The flux decays. It goes away over time, but it takes a long time. So if I don't know if I have a plot here, I don't think so. But if I put this as a magnetic flux for this time, it will just decay like this on exponential time.
Like most time, how much is long?
So this would be some exponential timescale t over tau, where tau is, say, about 100 Rg over c. This you can approximate analytically, and the main importance to obey the O'Hare theorem is that this is an exponential.
Does that depend on the reconnection rate?
Yes, exactly. Yeah.
It's not just Rg there.
No, you're right. So if you do this interesting question, I left it out of the talk, but if you do this with MHD, tau is maybe more like 500 Rg over C, and if you do it with PIC, it's about 100. This is a difference in the reconnection rate that you see directly in the decay time scales. Let's say PIC looks like this, MHD looks like this, PIC looks like this.
The PIC with real physical parameters, or the PIC you're on real charges and real masses?
So real masses in the sense that it's paired plasma, so there's no mass difference with ions here, but not real as in the sense that we're obeying this hierarchy.
So can you extend that to real masses? So
in a simulation, no.
No, just the extrapolate.
Oh yeah, I mean we did it for factor 10 up to factor 1,000, and
I understand, but if you extrapolate the mass and the charges to be real electron mass and electron charges, the value would be 500 Rg there, the power value.
The value seems not to depend on the ratio between these things. I mean, if you're asking me, can I do this for real parameters? No, I cannot simulate. But
you can, but it estimates the time scales power.
It's independent. It's independent of those scales. Yeah. It's a reconnection rate that sets it.
Which is,
as far as we know, independent of the.
same thing.
Yeah. But I mean, are you asking me if things change if we go to real parameters? I don't dare making that statement. Right. So if we go back to our accreting black hole, we actually know a little bit more about the field line structure if we look at the polarization. The main conclusion is that based on the polarization, we expect that there is some coherent poloidal magnetic field, like in this Blanford's-Nyack picture. There seems to be some vertical component of the field. You can see this from comparing these strikes here with the three toy simulations, no MHD here, but just a magnetic field that's been ray traced with a polarization ray tracing code. They see it looks mostly like this, so that would tell us there's some vertical field. Now, that vertical field has been thought about before by Ramesh Narayan, Igor Igoumenchev, and they thought of the idea that you could magnetically arrest an accretion disk if you can build up such a vertical field that can sort of stop the flow. It acts as a wall and keep the flow out for a certain period of time. It's again been simulated by Sasha Tchaikovskoy and others, John McKinney, and what you see is same picture as before. You have in orange you have the disk, and blue you have the jet, and here you see this vertical barrier, vertical field that's been built up. And it can indeed impede the accretion, at least transiently and non-axisymmetrically. Like it doesn't. What I'm trying to say is it doesn't put the accretion to zero. It just impedes it. Now, if you simulate this with very high resolution in 2D and you add the resistivity, then what you suddenly see is that if you zoom into the horizon, there is again this like vertical layer here. But you see that here, a very thin layer still persists, and that layer gets so thin that it starts to reconnect. You don't see this here because simply the resolution is not high enough to capture those thin layers near the horizon. So we could first do this in 2D, and Antonios actually here did very similar simulations in the less magnetically arrested regime, where you saw also reconnection along jet boundaries. So, but it would really required high resolution. I wouldn't even say it would require resistivity, it required high resolution. That's the trick. I will show this here. So this is the mesh refinement. So we use 6 levels to reach 12,000 by 6,000 cells. And that ensured us that the largest reconnection layers were captured by 10 cells over the width of the layer. And with largest, I mean RG size reconnection layers. So if you zoom in, you see this, like the turbulence is very nicely resolved in the disk. And if you go in further, you see reconnection layers on the horizon. You see even mergers of plasmoids here. And yeah, you don't even see the cells, but they're plotted here, but that should convince you that the layer is well resolved. So how does that actually work? If you go back to this magnetically arrested picture, in the standard accretion phase, you have a disk in pink here, orange, where the gas pressure, the ramp pressure, exceeds the magnetic pressure. So the disk can bring in magnetic field. This field can be turbulent, some colloidal component. God knows how that colloidal component got there, but let's not get into that. The field winds it up, you create a jet, and now you keep doing that over and over and over. So the field keeps winding up, the hole keeps winding up the field lines. So you're putting pretty much magnetic field lines here at the boundaries of the jet, because the field won't penetrate all the way here, because it's pretty much not easy to do that. So if you keep doing that, you're building up magnetic pressure here at the northern and the southern jet boundaries, until at some point that magnetic pressure really starts to push further inwards, and this accretion flow can get very thin. And now imagine this is the last field line that has accreted, and this was a field line that the field line itself doesn't know that it fell through the horizon. We see it cut off here at the horizon if we were able to see it, but the field line itself has no clue that it fell through. So this is still one and the same field line. So that tells you that here the field line has to be anti-parallel to itself, right? Because here it's connected, so ingoing, outgoing. So here you create naturally a reconnection layer, as long as you can make it thin enough, as long as you can squeeze it enough. And that seems to be what happens. And now what's interesting, I'll go back to the Wikipedia image. Now imagine the black hole is here on the left. So you have some loops falling into the black hole and some loops escaping from such an X point. These loops here, so imagine this is the base of the northern jet, base of the southern jet. Pretty much, I'm going to call it horizontal. In reality, they're toroidal field lines. But horizontal field lines, they create a little bit of vertical field. If the vertical field can escape, it will get like stretched out, expand, and it will build exactly this wall that we talked about before. So reconnection can create vertical field that can move outwards as long as it can escape the gravitational pull. And in that way, the reconnection layer can protect itself. It builds a wall that protects itself. Now that only works for so long until really Taylor type instabilities can go around the layer and penetrate it. But for that, you really need 3D simulations. So that's what we did. This is 3D simulation. And here you see that flux that we're talking about before. So you see the flux building up, building up, building up until it hits this point where the gas pressure becomes equal to the magnetic pressure, and then it quickly drops. And this drop here, this exponential time scale is magically the same as this balding process. So that tells you that it's not conclusive proof, but it's a strong indication it's really the reconnection and the reconnection rate that governs this, because it's exactly this as in the local experiment, which we found quite exciting. And if you now look here during this period, there is indeed a thin layer on both sides, now non-axisymmetric because it's 3D. And we can zoom into that. And then you see that also here, you have something that looks like plasmoids. In 3D, a reconnection layer is much more turbulent. Plasmoid instability may or may not happen in a similar way. That's a strong debate in plasma physics, but it's pretty clear that this layer is undergoing some instability. Whether you want to call it plasmoid instability or not, it's not important for the story here. What's interesting is that you see that the disk is really ejected by this vertical field that pushes outwards to different radii pretty much on the left and the right. So this tells you again, this is a non-axisymmetric process, but it creates a very strong magnetosphere region here, transiently, right? So the dark blue regions are the jet. So for MD7, for example, this jet has a magnetization that may be 10 to the 8, 10 to the 9. So there's a huge reservoir of energy that can feed this reconnection. So the reconnection is important to process that energy and power of flare, but it's also important in the cycle of the accretion. Right. So just to show that this was this was not easy. Resolving the reconnection, you required about 5,000 by 2,500 cells. This was at the time the largest GRMHD simulation ever done. It's about 1,000 times larger than EHT simulations, and that's not to say that EHT simulations are not good. It is to say that if you want to resolve particular physics, you need to do better, but it's not possible to do this all the time. So an important question is to figure out, what do lower resolution simulations actually capture of the physics? And the answer is it's not all that dramatic. I may get back to that later. This cost about 1 million GPU hours and 6,000 GPUs. So it's really a simulation that you can do once every so many years, and not just all the time. It was possible with this hammer code developed by Matthew Liska. It's GPU accelerated. With the CPU code, it would simply not, it wouldn't work. So, okay, now you think maybe, okay, problem solved, but actually the flare depends still on these kinetic physics that we're not having in this simulation: particle acceleration, radiation, and flare creation. So we didn't get much further, except that MHD tells you a reconnection layer forms in a highly magnetized region. That's about the only conclusion I would dare drawing like robustly from these simulations. This is what it looks like in 3D. So this is your accreting phase, where blue and green field lines are they're the same. They're both in the disk. They connect to the black hole, but here in the eruption phase, the green field lines are in this hot region. So the red gives you the temperature in terms of ion rest mass. So everything above 1 is relativistically hot. And the green field lines are the blue field lines are in the disk that are now pushed away. And here you see this is not a perfectly symmetric thing, because there's still some field lines reaching the black hole. There's still some accretion going. If you zoom in to those field lines near the horizon, you see an X point here, 3-dimensional X point. And you also see a 3-dimensional like little flux tube, which you may call a plasmoid, but it depends pretty much whether you want to. This reconnection has no guide field. You see all components either are 0 or go through 0. So there is no, so both the toroidal and the radial field reconnect here, which is important for the particle acceleration in particular. What's interesting is you can ray trace this in a simple way, as the EHT does. This is work done by Ripperda in Princeton. It's actually now accepted in MNRAS, so I should update my slides. And if you ray trace it, you will see something interesting. So this is pretty much calculating the light that is in the EHT band coming from the simulation. This is your, let's say, typical EHT image. And at some point, you will see the flare happening. So this is still accreting phase. And the flare happens about now. And like, how do you see now that the flare happens? The thing doesn't get brighter. Actually, the thing gets dimmer, right? The whole larger scale emission drops, and the ring that's left is pretty dim. And you also see this in the light curve. So the gray bands here indicate this such a flux eruption period. And you see that the photon flux in the sub-millimeter band and 230 gigahertz, it goes down during the flux eruption. And the reason for that, we think, is that the accretion disk is pushed away. So your disk is pushed away all the way to, say, 10 RG. The reconnection layer that's left there is too hot, pretty much, to radiate much in low energies. So it would give you X-rays or gamma rays, but not much radio. And there are some indications that this really happens in nature. This is from a paper by Maciek Wielgus with observation with ALMA. And during an X-ray flare, this is for Sagittarius A star. During an X-ray flare, you see that the sub-millimeter seems to go down, and then only afterwards it goes up. Whether that's statistically significant and whether that's really the effect that you're seeing right there, we cannot really say yet. But it's obviously very interesting to look at EHT image during flares to see if we can see this effect. Yes, Antonius.
The different modes are only radio or
Yeah, all radio different bands.
so
Yeah.
the X-ray we cannot see, it's just there you say.
Yeah, exactly. Yeah.
It's not.
No, it's not plotted on here. So another interesting thing that you could look at is not so much necessarily the dimming, but if the disk is pushed away, your ring would get bigger because the emission comes from larger radius. Right. So now let's get back to adding in more physics. How much time do I have left, Maria? Oh, perfect. Great. So what we can do is to keep solving Maxwell's equations, but then on top, we start solving particle equations of motion in curved spacetime. And there is a clever way of doing that because you can, if you know a general, like a standard particle and cell scheme, you know that it constantly solves equation of motion for, let's say, 1 billion particles, and it couples it back to Maxwell's equation, goes on and on. It's actually numerically pretty simple compared to MHD. It's just hard to resolve the scales. In GR, it's somewhat more involved because it's not standard and it's not trivial actually to solve those equations of motion on a curved background because you have a geodesic term. You have an additional gravitational force that comes in a geodesic term. And to solve that geodesic term together with the Lorentz force, you would have to come up with a Hamiltonian, discretize that, and then you have a discretized set of equations of motion that incorporates both forces. You can do it, it's very expensive to do. So Kyle Parfrey, Sasha Filipov, and Benoit Cerruti came up with a clever idea. What they actually do is they solve the geodesic term, which that is very standard. Ray tracing codes do it all the time. You can do it with a simple Runge-Kutta scheme or an implicit scheme, not hard. But then they realize that the Lorentz force, or in other words, let's say the gyration of the particle, happens on such small scales that the curved spacetime is not important for that gyration. So you can approximate it as locally flat. In other words, for every particle, you can come up with a local orthonormal basis of your vectors, and you can use your standard flat spacetime particle and cell scheme. Then you transform back and you do your geodesic evolution again. So it's an additional numerical step, but it works very, very well, and it's actually pretty fast. So that's a scheme that we're using, and what we could do, or rather, Alisa Kolesnikova for instance did, is we simulated GR-MHD accretion versus GR particle and cell. This is a 2D setup, no 3D effects. It is spherically infalling accretion, so there's no angular momentum, there's no disk, so to say, it's Bondi accretion. And there's just initially a colloidal field, or in the simplest case, even just vertical field. And then the vertical field, we gave some additional turbulence, but so it's a toy problem, but you can see the differences. So in the beginning, it still looks fairly similar. Now you get an eruption here, you get a thin current sheet, plasmoids on both sides. But here you start to see the difference already. And the difference here mainly comes from the reconnection rate. So because the energy is transferred here 10 times faster than here, and the material is pushed outwards, as long as it doesn't fall in, you start to affect the global scales of your infalling plasma. So even something tiny like a reconnection rate happening on a skin depth level has a global effect if you measure statistics of the accretion. So back to the flare. So this is the same simulation, and this is the density of the ions. So ions here had were a factor, I think we did up to 10 heavier than the electrons, so they're not real ions, so it was too hard to do. But what you see is that the heavier particles, they're all piled up in let's call it a disk for simplicity, even though it's not really a disk. And here in the region where you see the reconnection, the plasmoids, you see there is no ion density. So this is really only pairs, only electrons and positrons. Yeah.
Do you need sources of particles?
Yeah, that's right. Yeah.
Where do you do?
You kind of fake the pair production in the jet region. Whenever there is a significant electric field, E dot B, then you inject pairs. Later on, Benjamin Crampon and others have simulated not this accretion flow, but a simpler setup, also a real pair production, as in taking real probabilities and using Monte Carlo type methods to really inject in pairs. But it's parameterized, let's put it like that. But yeah, they're injected in these regions. And here you see this decay time scale, and you see that the particle cell decays much faster during flux eruption than the MHD. And here you see that the MHD is T over 300, something different than I quoted before. I don't really understand what's the difference, but what we found out recently, I don't have a picture, is that it depends on the spin. So the time scale depends on the spin. Paper to appear on archive. Particles. Faster, yeah, it's steeper because the reconnection rate is higher, pretty much. But it's not an easy factor 10 difference; it's a factor few difference. So we're still trying to understand why that is. I'm sure it's global effects, but I don't know what exactly. Right, and also what's interesting to see is that you in the current sheet, but also in the ejecta, you form a non-thermal tail. So this could really power the tail is of course not realistic in the sense what you were asking before. The scale separation, the mass ratios, the numbers are not realistic. So you would have to extrapolate this to realistic numbers to see if this could do a flare, and then radiation physics becomes important. And we pretty much can do the radiation physics with pen and paper, as in, if we assume that the reconnection here is in a high sigma regime, there is no guide field, then you can calculate the cooling time, and the cooling time is very fast in a fast cooling regime. So synchrotron photons that are emitted here, they can then pair produce, and those pair produced particles, they may emit secondary synchrotron radiation. But the accelerated particles may also upscatter existing seed photons and their own synchrotron photons. So we have a whole number of processes here that we think that can be important at different levels. And we can simulate that. Haik Jacobian did that with particle and cell simulation, now ignoring the black hole, just 2D particle and cell, but including the radiation. So inverse Compton, synchrotron, and also pair production. And in that way, you can predict a flare spectrum pretty much if you assume that this is happening. And what you see is that the synchrotron emission gives you a peak here that would roughly give you X-rays, and the Compton scattering, and this is mainly inverse Compton on seed photons. So this depends on what your seed photons are like. We have some observational constraints, but it's not very well constrained. But the inverse Compton scattering of seed photons can give you a gamma ray component of the spectrum. So this is pretty cool, and I wouldn't say we have solved the flaring mechanism, because there's a lot of physics that's not fully understood or incorporated. There's discharge physics that we don't understand or incorporate yet, but this mechanism could, in principle, give you gamma rays, which is quite cool. How much time do we have left now? 5 minutes. Okay. So I want to quickly then go to Sagittarius. Sorry. I want to quickly go to Sagittarius A star to see if a similar story holds, but I don't want to go through all the observations. I pretty much just want to show you. This is work by Sean Ressler, who modeled the flow onto Sagittarius A star from about 30 Wolf Ray A stars blowing winds to the center. It was really expensive simulation because it incorporates so many scales. Main conclusion for this message here is that even if you do that, the inner region can become magnetically arrested. So you can, from large scales, bring in so much flux that the inner region becomes magnetically arrested and does those eruptions. Right. So let's model this as a spherically infalling plasma with the Bondi accretion. It's what Sean did by himself. And we did this now at slightly higher resolution and really focused only on this eruption. We put a lot of mesh family really here on this eruption. And here you see the field lines, and you see that they also reconnect. And let me see. I have a better video, but I think I removed it. Anyway. So what you see is that even in a spherically infalling case, the same as with the particle cell, but now in 3D, you get those eruptions and they blow flux tubes, so vertical field into the disk. And what is now interesting is that those flux tubes, they will have some orbital velocity. Even if the accretion disk doesn't have angular momentum, the field that's being pushed away, like these vertical lines here, they get some orbital velocity from the ergosphere, pretty much. So you can see what they do. Let me skip all of this. Right. So here you see those flux tubes. Not yet. And here you see the reconnection going on, the plasma heats up. And now we see it pushes this vertical field. This is what we talked about earlier in the cartoon. It pushes vertical field into the disk. And you see on the left, there's no such tube. The disk is just turbulent field, toroidally dominated. And on the right, you see there's very coherent vertical field. It's the same like field that protects the current sheet in the magnetically arrested state. And now we can zoom in onto that tube of vertical field and see what it does. It's this thing here. You see the magenta field lines. So these are two cuts, equatorial plane, colloidal plane. And you see that the vertical field here is anchored in a low density region. So this is density. Red is the disk. Blue is the tube. So the tube is both hot and low density. And it orbits. It goes around the black hole. And now think of this situation and think of your fluid dynamics class. You have high density disk here. You have a low density tube here. And gravity points towards the black hole. This thing has to be Rayleigh-Taylor unstable. And that's what you see. You see Rayleigh-Taylor fingers here forming that protrude the tube. So what this can do is it can mix disk material into the tube, protons, for example. But the tube itself is still dominated by paraplasma because it's what came from the jet and then is contained in this tube. So we may mix paraplasma into the disk here a little bit, but more interestingly, we may actually mix protons into the tube, and these vertical field lines, they act as a highway, right? Like put a proton on a vertical field, it will like move upwards. So if you, if you simulate this again with particle and cell, this is just like, let's say, simulating this layer here with the local 2D box. You see it goes indeed Rayleigh-Taylor unstable, and you see, let me play this video again. You see that those particles, so the dots are particles, they get sucked into the Rayleigh-Taylor fingers. Here, the Rayleigh-Taylor clues, they reconnect on each other. And you get a secondary acceleration of particles. And you see this here in the spectrum. So you see non-thermal tail of this is again paraplasma. And those particles, they can accelerate and they can potentially explain the infrared flares as observed by gravity. And again, I'm not claiming that this is the solution, but what is intriguing to me is that we have a thing that's rotating, which is what gravity saw. We have a mechanism to accelerate particles, which doesn't rely necessarily on reconnection in the near the horizon. And roughly, the tail matches with what you would expect from gravity observation from infrared. Again, that's just an energetics argument. It's not the full solution. Right. So the last thing I wanted to show is, and I'm mainly showing it because I was talking with Maria about it before. So these are two of such tubes. This is an older one from an earlier eruption, and this is a younger one that just formed. And here you see again the same picture. You have toroidal field, and you have a vertical field and tube. Here, Rayleigh-Taylor fingers mixing, and those vertical field lines, they connect all the way to the jet. So those field lines here at high altitudes, the vertical field from the tube with the wound-up field of the jet, they interact, and this could act as a proton injection mechanism in the jet. So this is something we didn't publish, but we're thinking about like how that could work. It's very interesting both to see if this could mass load the jet, but also whether this could act as an ultra high energy cosmic ray acceleration mechanism. And maybe one last thing. This also seems to happen in thin disks. This is work by Jibba Musoke in Toronto. If you simulate a thin disk with a lot of colloidal field, you can truncate the disk. And it looks a lot like a magnetically arrested disk in the inner region, while you have like an ejected sort of thin disk, coronae disk that's being pushed away. But here, flux eruptions are happening continuously. These are all little flux eruptions. And so this system is able to maintain a current sheet on the horizon and is able to keep pushing vertical field outwards for a very long time. Whereas a thick disk, the one that I've been talking about so far, does this only transiently, episodically. So this is an interesting way to maintain an equatorial current sheet for a long period of time and have those vertical field lines that connect to the jet for a very long. Something we're looking into right now, and I'm quite excited about. That's all.
So let's see from the online participants if you have questions. Can you raise your hands? Yes, there is one question. If you can repeat it, maybe. Yes, please,
Okay.
Nick.
Hello, I'm Nick Kilafis. Though I joined a bit late due to the previous engagement, I enjoyed your talk thoroughly and I'm impressed with the simulations. Congratulations.
Thank you.
I wanted to ask you, I'm also doing modeling, but not as heavy as you. I'm more geared towards the observations. And I wanted to ask you if you have considered at all, or as yet, correlations that have been observed in black hole X-ray binaries, NAGN, but let's stick to black hole X-ray binaries. So the most well-known is the radio X-ray correlation.
Yeah.
Have you thought about it or addressed it?
Addressed it, definitely not. We have thought about it, particularly due to this last slide. If you have enough colloidal field in your disk, then it seems that you can have a state where you can launch a jet, maintain a thin disk, and form a hot coronal region here. If you don't have enough colloidal field, in other words, if your disk is toroidally dominated, then you don't do this. Then you don't form a jet, and you just have a Shikura-Sunyaev type disk. So this is about as far as we got in thinking whether you could explain that there's sort of different states of X-ray radio correlation. Like you would have a strong radio jet if there is a strong X-ray corona, and if not, then there would also not be a strong radio jet. We're now looking into more depth because the thing is in these simulations, it all depends a lot on your initial conditions. So I don't necessarily trust that to represent reality. It also depends a lot on your radiation physics and so on, but the initial conditions have a strong effect. So what we're trying to understand now is if you can do this in a more self-consistent way by putting not such strong colloidal magnetic field as an initial condition and see if you can still find this relationship of an X-ray emitting corona and a strong jet. That's about the level that I've thought about it. So it's probably not very satisfactory.
Yeah. Keep it in mind though, because as you know, it's much more easier to explain, one quantity than a correlation of two quantities.
Exactly. Yeah. Exactly.
And so correlations impose significant constraints on models. And then while I'm at it, and I will finish here, the spectra are relatively easy to be reproduced. because they are, Comptonization spectra are infinitely degenerate.
Yeah.
So you just, if you leave me freedom, I can reproduce any spectrum that you want.
Right.
But the spectra have other properties. For example, the hard X-ray photons come later than the softer ones, so there is a time lag.
Yeah.
Have you seen any of that, at least have you seen it at all in your simulations? That is, that the harder spectra are coming out later than the softer ones.
Are you talking still about XRBs or also about low luminosity AGN?
Binary X-ray binaries.
Right. No, we haven't seen it. That doesn't mean it's not there, but I'm a careful plasma physicist, so I don't dare concluding these things based on MHD simulations. That's the short answer. So what we're trying to understand is whether there can be particle, or let's say there can be emission sites that you can trust in MHD, from which you could then build a model for the spectrum and the time lag, because if the mechanisms in the MHD simulation happen at different times, you could build a model for the time lag. But again, I don't dare saying anything conclusive simply because I don't trust yet what we're finding. I'm being conservative.
Okay, it's good, but on the other hand, in the future, maybe you would like to consider these aspects and see if your model explains them, because the observations are indisputable.
Yeah. No, we're well aware. So it's definitely on our mind, and I fully agree with you. I think maybe this is a good lesson also for students. Look at the observations first before you run an expensive simulation, and think about what you know robustly from observations before you start modeling. I think that's
okay. Yes, this is everybody's decision on how to do research. Yes. Okay, thank you very much. I really liked it, and you've done very good work. Continue it.
Thank you.
Yes, so questions from.
I like very much your picture. I have one component that keeps crossing the horizon, which is an electron-positron jet, which never goes to zero because those flares never go down to zero plus eruption.
Yeah.
And another component that enters the disk and for some time at least gets replenished with photons from the disk.
Yeah.
So downstream, you have something that you have two parts in the jet: a sheaf, a proton sheaf, a plasma sheaf, and an electron-positron core. But the origin of this sheaf is variable. After a while, you will not keep replenishing.
Yeah, that's right.
So what you're describing, which is extremely interesting, you expect to see downstream in the jet and see this variability, something changing downstream. Any comment on that? You can associate your time scales of 1,000 RG or a few thousand RG with things happening downstream in the jet.
Yeah, there are a number of things that, again, we've been thinking about. One is, you see during those eruptions, you see pretty much the jet going all the way to this, and then once it starts accreting again, it will do this, and then it builds up again. So there is like a spatial movement of the jet that's interesting. Then the second is, those eruptions, they also perturb the field lines of the jet. So because they sort of bump into the jet boundary, so you see waves that may get nonlinear and may travel along the jet. So there are some signatures of this, and the eruption timescales are of the order of, let's say, 100, 200 RG over C, but the accretion phases to build up are like 1,000 to 2,000 RG over C. So there should be something distinguishable, I think, as you say. What I left out of this story, and it's something that I don't fully understand myself yet, is whether what we're seeing, what I showed today, is it a steady state? Is it something that we can trust to do long-term predictions? So if you simulate this for a very long time, will you end up with hundreds of flux tubes that pretty much make your whole inner region fully magnetized, still connected to the jet? So we now did this high resolution simulation, instead of 10 to the 4 RG over C, and ran it till 10 to the 5 RG over C. And you see that flux tubes live for a pretty long time. So getting back to your question, it means that you could have a fairly continuous injection, because all those flux tubes, they keep connecting to the jet and they move outwards, so they connect to larger and larger radii and larger altitudes. And I think it's something we didn't understand yet, as in what is a long-term steady state for such a magnetically arrested disk? I think that's a very important question to understand before concluding more, but it's extremely expensive to simulate.
We've seen this effect since 2011, for simulation.
Yeah.
This flux are happening very
Yeah.
clear, and the issue then, 15 years ago, was whether you have reached a steady state. Because if you look
Exactly.
at the coloring of this disk, looking from a ball,
Yeah.
it was red, then it became orange,
Exactly.
then it became yellow, because the magnetization kept
Exactly.
dropping,
Yeah.
and then the question is what happens after, 1,000 times that.
Exactly. Exactly.
Everybody thinks they're talking about steady state, but you're asking yourself, and I like that you're asking yourself whether we have reached steady state, what the steady state will look like.
Yeah.
Very good that you're discussing those things.
Yeah.
Because the question was there from the very beginning.
Exactly. Exactly. I think now we're at the point that we can both run for long enough. And so the issue is not only time evolution or time resolution, if you want, but also radial, because those tubes, they will, if you don't have high enough, like your cells, they look like this, right? So like the more you move outwards, the less you resolve your physics. So those tubes, if they end up here, they may be diffusing, while in reality they wouldn't. And now we can reach resolutions up to 100 RG that sort of maintain those tubes. And it turns out they're much longer lived than in the earlier simulations. But again, yeah, inconclusive. We're trying to understand, and I can show you a video I didn't put in the slides, but it seems, long story short, it seems pretty interesting to understand this a bit better. And I think that we're not at the final answer yet, whether there is a steady state.
Very nice thought, very nice work. So I'm curious, you said several times, and it's in the literature films write like this, that all these eruption events push the disk outwards. Have you seen, I don't know, velocity plasma fluids that they have velocity like this or not? I mean, does really the plasma is pushed out or something different?
Yeah, there's absolutely a positive radial velocity during an eruption. And I have a video, but again, not on the slides, I can show it to you afterwards. But you see a pretty significant change, as in during that whole accretion phase, during that 2000 RG over C, you see only negative radial velocity, as in going inwards, except in the jet, of course, there's a pointing flux, but in the disk, it's all inwards. And then you get a flux eruption, and it's all radially going outwards. And then afterwards, you're left with the wind. It looks a bit like a butterfly. And around the equator, you get again radially inwards. And I think that's due to Rayleigh-Taylor instability. So there are like three phases, if you want, that we see.
So even when you have this outward, let's say, radial velocity at the equator, at this layer that you were showing, still matter is passing through.
So it depends on
Does accretion continue even slightly in this layer that you are resolving there of this plasma?
So it depends whether you want to call it accretion. So in the reconnection layer itself, the only thing you're accreting are plasmoids that cannot escape the gravitational pull. That's really, really minimal. In other words, if you do a 2D simulation of a magnetically arrested disk, your accretion really drops to zero pretty much, because the plasma is insignificant in terms of accretion. In 3D, it's not that thin layer that is accreting, it's a stream, a spiral that goes around the flux tube. So through Rayleigh-Taylor instability, it manages to sort of go around or through, however you want to see it. And that gives you a non-zero accretion rate. So it depends how big your flux eruption is, whether it covers the full 2 pi or nearly the full 2 pi or only a fraction of it. We also see small flux eruptions that only cover a quarter of 2 pi, a quarter of the full angle. You have a small tube and most of the thing is still accreting. You have a small drop, it'll look like this, it's overall accreting, and then it does like this. And a large flux eruption will really do this, but it won't go to zero. It will never be absolutely zero, I think.
Yeah, I have a bunch of questions. I was really interested in the jet in the first place, but it turns out that I'm also working on YSO. And we do have right now with the destabilization in the simulations that looks really like muon, although we are not relativistic. So my first question was how much you rely on the fact that it is relativistic, or I mean, is it that important that it is relativistic, except that you apply that? The second question would be about the flares. I was intrigued because we also work on the fact that flares can ionize and reduce MRI in the goods very efficiently new stuff.
Yeah.
And surprisingly, giving emitting rate that are exactly those we need for the jet and the accretion.
Yeah.
And trigger accretion, because that's usually people assume that this is fully ionized close to the star, and
Right.
and when you look carefully, it's not that clear. But
Yeah.
if you have the flares, so the second question was, if you have looked at the back reaction of your flare, is it too early in your simulation?
I would think if you're talking about any Newtonian physics, let's say solar or protoplanetary, I would say accretion is about 30 years behind. So we're kind of happy that we can do ideal MHD at this point. I think it's important to look beyond that, but it hasn't been done, I think. So I think what I'm showing was the back reaction of the flares is in the flux eruptions on the accretion flow. That's something that we're looking into, but anything related to the real flare as in the light, right? Because what I'm showing is only, I didn't show a flare, I showed a flare mechanism, or there's no photons here whatsoever. So
but you have a spectrum which goes to high gamma ray. So I was
it's just a two-dimensional particle and cell simulation where there's no black hole, no accretion disk whatsoever. Right? I'm just that spectrum I can only make if I say I do a separate simulation where I assume that we have reconnection on the horizon, but I pick out all the black hole and the disk physics.
But we did trigger as it does. We do have intermittent accretion. And the thing is that first may trigger, you were talking about this earlier, and my question was, don't you think it may trigger accretion again? I mean, even if you have omitting accretion, the fact that you have the flares may start a new accretion on the black hole.
For what you're asking, do you need photons interacting with the plasma or not?
It's not the photons, it's the fact that you have non-thermal particles
Non-thermal particles, right?
that are entering the
And they are yes.
and entering the disk,
Yeah.
and they will ionize, and they will
I see.
hit the plasma there, and then trigger turbulence.
Yeah.
And this can help to have again
Yeah.
accretion, although there it's
So those are effects that we cannot yet model. Definitely not in MHD, and in PIC we only did those. We can do one eruption in a 2D toy model. Even if we can model them, I'm not sure it's exactly the same. This magnetically arrested state is pretty special. I don't know. I also don't know if it's representative. It seems to match with EHT observations, but can fit an elephant to the EHT observation, but it still match. But what role the MRI plays in reactivating the accretion has always been, people have always said it's not important because the MRI doesn't act at highly magnetized plasmas. I think that's wrong. I think we understand now that the MRI is important in the disk beyond that tube, but how exactly and what role those tubes play, because they're pretty much big spoons in your disk or stirring up the disk and creating turbulence. It's a great question. I don't have the answer. Your first question is also interesting, but it's simple. No, you don't need any relativity for any of this. Yes, for the specific jet launching, and like here it gets very magnetized, you need gravity. But for all the disk physics, I would argue no, don't. There is a paper by Takasao for protostellar flares. It's exactly the same.
Yeah, of course, we are comparing now simulations to the same.
Yeah. I think it's very simple.
But in Takasao, there is not that intermittent. The point is that we have simulations that are quite new in the sense that we do have accretion, then there is this barrier that stops the accretion, but then accretion starts again.
Yeah.
And it happens that we don't know if it's perfect, but there is a one object which is R1 tau that are two states, quiescent and active. And the idea is that people say that's probably because sometimes you have the jet that clears everything and you see the star and the other you don't.
Yeah.
And it really looks like what you have in X-ray binaries, you know, what you have the I state and low
Exactly.
state. So the question was, maybe this mechanism that you have is not specific to relativistic object, but may apply to other accreting objects.
I totally agree. Yeah, it's very cool.
I have one comment and maybe two or more questions, but first going to the comment, because you mentioned or you showed about the two-dimensional peak simulation by Young for M7, and you showed this very nice spectra. So I think that these spectra were not computed from peak simulations directly. Am I wrong?
That's right. We have both. Yeah, I showed the analytic one. Yeah.
Because recently we're looking into the results of having some input from three-dimensional peak simulations, and the picture is very different when we take into account the fact that there are other channels of particle acceleration not found in 2D peak simulations. So this was a comment that even though these are kind of state-of-the-art 2D peak simulations, like new 3D peak simulations might show a different picture.
Absolutely.
Regarding also the electromagnetic spectra of
Absolutely.
and the question, the second one, was related to the acceleration time scale instant in Vladimirs simulations. How fast did these test particles accelerate? Were you able to measure it?
Test particles in.
So this peak simulation or the kinetic simulation of the serial flow, and there were some test particles that were mixing from the.
Oh, the Rayleigh-Taylor one. You mean? They were not even test particles. There were actual full peak particles, but the same thing.
So what was the acceleration rate of these particles?
Yeah, good question. I think first of all, let me say that your first comment also applies. This was two-dimensional Rayleigh-Taylor. I think the reality would have to be 3D, and you would need an ion component. The acceleration mechanism is still reconnection. So it's similar as in a regular reconnection layer. The difference would mainly be, I think, that the cooling time is slow, because we're talking about infrared photons. So the cooling time would be long. So what we think is that those particles would pretty much they would orbit and do more Fermi type scattering while they're radiating, which makes it a complicated problem. So I'm not at all convinced that those 2D simulations give you the full answer. It's pretty complicated.
And from final one was related to this very nice quasi-periodic reaction that we were showing to us. So you were claiming that this is a clearing mechanism, and this could potentially be related to some of the X-ray pairs that we see in the tertiary star. So I was wondering if this is true, whether or not we should search for quasi-periodicity in these X-ray pairs, because as far as I'm aware, I don't think that these pairs happen in a quasi-periodic way. So you have a comment on that?
Many. Two main comments. One is, I think, and this comes back to the earlier discussion about quasi-steady state, I don't think those mad eruptions are as periodic as they look like. They happen roughly on every 1,000 to 2,000 RG/C, but they're different sizes. They different length scales, both the eruption and the time in between. And also the current sheet that you would form may not always be just like a pulsar current sheet. It may not be beaming into your line of sight pretty much. Like this thing is, you know, so it may very well be that you miss a flare, or that it would just not, the current sheet would not be big enough or whatever. That's generic, does not include Sagittarius A-star, it's a generic comment. Sagittarius A-star specifically, if you do the, and this is also why I didn't talk about that specifically, if you do the energetics for what we know about sigma near the black hole, we pretty much know like pair production is not very efficient near Sagittarius A-star. It's very hard to reconcile that with reconnection giving you any X-rays from that mechanism, unless the magnetization is fairly low, below 10 to the 4. So either something that we haven't simulated yet that would give you lower magnetization than what we find, because we find it to be at the floor, which is okay. It's not 10 to the 8, but we know in reality it would be. Or the X-rays would have to come from something else. And one thing that we have been thinking about is those Rayleigh-Taylor instabilities that can accelerate particles that may then upscatter on the turbulence and then give you an X-ray flare. And an interesting thing is that would give you more stochastic flaring, I think, as you say, but it would always be related to infrared. And there is some X-ray infrared connection in Sagittarius A-star, but it's not very obvious. It's not, if you talk to observers like Daryl Haggard, and she's not at all convinced about infrared and X-ray simultaneity. So yeah, big open question, but very interesting to think about. It's one right behind you.
Quick question. Have you considered including radiation in your kinetic simulation, interaction of particles with the photon field? And if yes, if you have a paraplasma that adds an extra force, you have a proton electron plasma that includes that it introduces a difference of velocity between the components, which acts as a battery. And have a theory, the cosmic battery, that generates magnetic field. So it will be very interesting to see the cosmic battery operating. So do you have any plans to include the radiation, interaction with radiation?
Yeah, definitely. Those plans are there. They're not mine. They're like Heika Kobian, Sasha Filipov. Well, those two mainly were pioneering that. There is the thing is that those GRPX simulations are extremely expensive, but the code is very non-efficient. It was in Fortran, it's called Zaltron, like code developed by Benoit Cerruti. So it didn't really allow you to do 3D, include radiation and so on, even though we know how to do it like numerically. So now there's a new code called Entity, which is GPU accelerated. It's going to become public very soon. So if someone wants to use it, definitely should. There's GR, there's inverse compton scattering, there's pair production, there's synchrotron radiation. And with the GPU, you're going to be able to actually also add in ions. And either go to 3D or go to electron ion plasma in 2D, for example. And hopefully you can get closer to the type of things that you're thinking about. Yeah.
If there are not any other questions, let's thank our speaker again.